Okay, now that we've learned about some of the key aspects of projectile motion, so horizontal component of velocity is constant, the vertical component of velocity is solely responsible for how long it takes to get to the top of its flight or how long it stays in the air for, we can start finally doing some calculations. So you're going to be calculating the time of flight for when a projectile is launched horizontally, straight off a surface. You're going to be able to calculate the time of flight, and the max height for a projectile when its launch height is the same as the landing height. So if it's on the ground, launched and lands back on the ground. So yeah, when the launch height is the same as the landing height. And then finally, you're going to be able to calculate the horizontal range. So range is basically just the total distance it's traveled horizontally. So calculating time of flight. Now, these are our equations of motion. We're going to treat our components of velocity separately. Now, our first one is a horizontal launch, and we're going to be calculating time of flight. So a vortex is launched horizontally at a velocity of 20 meters per second. So it's launched horizontally. So we're given the horizontal component of velocity, 20 meters per second off a balcony. The balcony is quite high, 30 meters. So our displacement is 30 meters up in the air. Now calculate the time of flight of the vortex. Now, in general, my coordinate system is usually plus is up and down is negative. Calculate the time of flight of the vortex. So time is what we want. Launched horizontally, so that we have the horizontal component of velocity. Oh, what's the initial? So that's our initial horizontal component of velocity. What's our initial component of vertical velocity? Initially, there's none. There isn't a. So the vertical component. So the vertical component of velocity initially is going to be 0 meters per second. So vortex is launched horizontally, velocity 20 meters per second from the balcony of a building at a vertical height. So we've also got, we want to find the time of flight. So how long it's going to take the vortex, because remember it's going to go like this. It's going to hit the ground. So we want to find the time of flight. So what we can do is, we know the vertical component of how far the vortex has dropped. So the displacement in the vertical direction is going to be that it's been displaced 30 meters. And it's actually going to be negative 30 meters based on my coordinate system. So the vertical component of displacement is 30 meters, or negative 30 meters. So we've got the vertical initial component, we've got the displacement, we've got time. There's something else that we always have. We always have the acceleration, and that's going to be acting downwards at 9.8 meters per second squared. So calculate the time of flight of the vortex. So we've got time, acceleration, v0, and displacement. So if we look at our four equations, we've got displacement. Which ones have displacement? So this one, wrong, could be this one. We've got acceleration, we need time, we've got v0. Yeah, we've got everything. This one, we don't have the final speed, so we can't use this one. So it must be this one. And we want to find the time of flight. Now, what's the initial component of vertical? So remember, everything, whenever we're trying to find time of flight, we're only considering everything in the vertical direction. So everything in the up and down direction. So initially it has a vertical velocity of 0. Its acceleration in the vertical direction is negative 9.8. The displacement is 30 meters. Because remember, it doesn't matter if it's launched horizontally. All this vertical component is solely responsible for how long it's going to take to get to the ground. So we can use this equation, but to make it easier to rearrange, the initial velocity is 0. So we're left with s equals a half at squared. And hopefully we've had some practice at rearranging, so we can rearrange that quite well. So we're going to times both sides by 2. So it'll be 2s, divide by a, and then finally square root. So the time is going to be 2 times the displacement, which is negative 30, divided by the acceleration due to gravity, which is negative 9.8. And if we chuck that into our calculator, we'll get that the time of flight from being launched horizontally to hitting the ground is going to be 2 times 8 is 2.47. And because we only have 2 significant figures, well, actually, do we have 1 or 2? I'm going to say we have 2. So it'll be, it's really, if you type it into your calculator, you get 2.47 meters per second, but to 2 significant figures, it's 2.5. Meters per second? No, it's time. 2.47 seconds. So 2.5 seconds to 2 significant figures. So if we launch a vortex at this speed, 20 meters per second, then it's going to hit the ground after 2.5 seconds. And realistically, if we just drop something off the balcony at 30 meters high, it's also just going to hit it at 2.5 seconds. The fact that we're launching it horizontally makes no difference. So that's the time of flight for a horizontal launch. Now, launch height equal to the landing height. So launch height, landing height. So a golf ball is hit from the ground with a velocity of 25 meters per second. So that's its initial velocity at an angle theta of 35 degrees above the ground. So that's our angle. The effects due to air resistance are negligible, so we're not going to consider air resistance. Calculate the time of flight of the golf ball. So when you're doing a launch at an angle, okay, what we need to do first is we need to find the time of flight up to its peak. So what we can do is the following. We're barely given any information. All we're given is the velocity and the angle, but we can actually work out how long it's going to take to hit the ground. It's total time of flight. The way we're going to do this is as follows. First, we're going to work out the vertical component of velocity, because the vertical component is solely responsible for time of flight. So we're going to do v sine theta. So v, which is 25 times sine 35. If we type that into our calculator, 25 times sine 35, we'll get 14. And this is going to be the 3 significant figures. So 14, actually, I should say, keep your things to more decimal places, because all we're actually trying to find is the time of flight. So we should actually keep this to quite a few decimal places to keep our answers more exact. So that's our vertical component of velocity. Now, time of flight, the way that we tackle these is we find the time of flight to the top of the time it takes to get to the top of its motion, and then we double it to find its total time of flight. Now, what's the vertical component of velocity going to be here? Hopefully you answered 0 meters per second. So at the top of a flight, its vertical component is going to be 0, because at that very split second of time, its vertical component of velocity is going to be 0. So we have its initial, this is actually its initial velocity, really. This is its initial vertical component of velocity. This is its final. We have acceleration due to gravity. So we have 3 things, 1, 2, 3, and we want to find time. So we have 3 things and we want time. So which ones have t in them? This one doesn't. These 2 have time in them. Now this one has displacement. We don't have displacement, so we can scrap that one. So this one here, v equals v0 plus at. And we can rearrange this equation for time, because we want time of flight. So we can take v0 from both sides, so it'll be v take v0. And we can divide by the a. And we'll get the time is equal to v take v0 divided by a. We can then substitute our known information into our equation, and our final velocity is 0 at the top of its path. Subtract our initial velocity, which is the 14.3394, divided by acceleration due to gravity, which is negative 9.8. If we substitute, if we type that into our calculator, we're going to get 1.46 seconds to 3 significant figures, which is what the question is given in 3 significant figures. This 0 is significant. So,
okay, I found this on the web for a 0.
theory, sorry. So that's how we find the time of flight to the top of its peak. Now, to find the total time of flight, which I often do as TOF, it's going to be 2 lots of that. And actually, I shouldn't have rounded it. That's my fault. So really, it's 1.463. 1.4632 seconds. Sorry, I jumped the gun. And now it's going to be 2 lots of that. So 2 lots of 1.4632. So times that by 2, and we'll get 2.93 seconds. So 2.93 seconds. It's actually 926, rounded up to 2.93 seconds. So the golf ball will be in the air for a time of flight of 2.93 seconds. Only round right at the end. Otherwise, you should keep your answers nice and long. Alright, I have a couple more examples to do. Our next one is the max height reached by the golf ball. So this is the exact same context, same golf ball. Golf ball's hit from the ground with a velocity of same 35 degrees. Calculate the max height. Well, the golf ball from before, we want the max height up to the top. So this here is the displacement of the golf ball. So we want the vertical component of displacement. Now, to do that, well, what do we have from the previous slide? Displacement, do we have the initial velocity in the vertical direction? We do, but acceleration in the vertical direction, and we've got the time. We do have the time to the top of its height because we've got that as 1.463. So, to find the displacement, we can use this equation here. So it's going to be S equals V naught T plus a half AT squared. So our initial velocity, if I go back, was 14.3394 times by the time of flight. Oh, went the wrong way. 1.4632. Whoops, I went the wrong way. 1.4632 plus a half times negative 9.8 times by 1.4632 squared. Oh, and if we type all that into our calculators, bit of a mess. 14.3394 times by 1.4632 plus a half times negative 9.8 times by 1.4632 squared. We get about 20 meters. So exactly we get 20.125, which is 20.1 meters. So the max height reached by the golf ball is 20.1 meters into the air vertically. Couple more examples. Now this equation isn't on our formula sheet, but easy to remember in multiple ways. But the horizontal range is simply the horizontal component of velocity multiplied by the time. So the reason being is there's a couple reasons. There's a couple different ways you can think about it. So if we look at this equation here, the half AT squared, well, there's no acceleration in the horizontal direction because there's no forces acting, so it cancels out, and we're just left with that the horizontal range is the horizontal component, which is its initial velocity because it doesn't change, times by its time of flight. It's time. Now, that's the easiest way to remember it. We'll just go with that. So, same context, golf ball, 25 meters per second, 35 degrees. The effects due to air resistance are negligible. Calculate the horizontal distance the golf ball travels. So if we want the horizontal distance, it's going to be the horizontal component of velocity times by its time of flight. So it's going to be, I don't think we actually worked out the horizontal component. No, we didn't. Okay, so we need the horizontal component. The horizontal component of velocity is v cos theta. I'm just going to do it in one calculation. V cos theta times time. And v is 25 meters per second times by cos of 35 degrees times by the time of flight, which was 2.93. Yeah. So times by 2.93 seconds, and therefore the horizontal range will be 25 times cos 35 times 2.93 seconds. So it'll be 60.0 meters. So it's travelled 60 meters. Its max height was 21, I think. Yep, 20.1, and it traveled 60.0 meters. Final question, and get you to do some practice problems, is that a soccer ball is kicked off the ground at a velocity of 12 meters per second at an angle of 40. So 40 degrees off the ground, velocity was 12 meters per second. Calculate the velocity of the ball after 1 second of it being in the air. Draw a vector diagram to assist you. Okay, so velocity, if we want the total velocity, we're going to need the horizontal and vertical components of velocity. Now, we don't know if after 1 second it's still traveling up to its max peak, or we don't know if it's coming down. We don't know yet. So we need to do some investigating. So to find its velocity here, okay, wherever it is, whether it's up here or down here, we're going to need its horizontal component and its vertical component, or its vertical component and its horizontal component. Now, what we can do is, we know that the horizontal component doesn't change, it's constant, because there's no forces acting in the horizontal direction. So the horizontal component of velocity is v cos theta. So it's v, which is 12, times by cos of 40 degrees. And if we type that into our calculator, we get 12 times by cos 40, and that's 9.1925 meters per second. So that's our horizontal component of velocity. Now, to find our vertical component of velocity, well, we've got the time. We want it after 1 second. We've got, well, we can find the initial component of velocity, because we can find it here. We can find our initial component of velocity. So let's calculate also our vertical component, which is actually our initial. So that's going to be v sine theta, which is going to be 12 times sine 40. 12 times sine 40 will give us 7.71345 meters per second. Okay, so we've got the initial velocity. 1 sec, so we've got a time. So we have a time of 1 second. We've also got acceleration is negative 9.8 meters per second squared in the vertical direction. So we've got v, initial velocity. We want the final velocity. So we want final velocity. We've got the initial velocity, acceleration, and time. That one's easy. We don't have to do any rearranging. So we can use this top equation here. V equals v naught plus at. So our initial vertical component is 7.71345, and then we're going to add on negative 9.8 times for 1 second. So if we type that into our calculator, you might be able to see it's going to be a negative number, 7.71345 plus minus 9.8 times by 1. So it's going to be negative 2.08. We'll just go 7. 8655. So negative 2. Well, that means that it's acting downwards. The negative is important, so it's downwards. So our ball has actually gone past its peak, max height, and it's actually on its way back down. So it's a little bit. So it's not going very fast though. So start off at 7.7, reached 0, and now it's negative 2. So it's somewhere around here. So we can work out its. So basically, our vector diagram to assist you would be something like the horizontal component, and the horizontal component hasn't changed. It's quite large. It's 9.1925 meters per second, and our vertical component is downwards, so it's 2.08655 meters per second. Whoops. And that's our vertical component of velocity. So what we can do is to find our resultant velocity vector, or our velocity after 1 second, we're going to use Pythagoras' theorem to find v, and our angle, we're going to use trigonometry. So remember, you can skip straight to v equals the square root of our horizontal component, which is the horizontal component squared plus the vertical component squared. Look back over your notes if you're not sure why, but this is just Pythagoras' theorem. So it's going to be 9.1925 squared plus 2.08655 squared. You don't want the negative there because it's Pythagoras' theorem is dealing in distances, so you don't want the negative there. So not the negative 2. And that, if you type that into the calculator, you will get the square root of that answer, 9.42. So it's 9.4, or 3 rounded to 3 significant figures. Oh, we only want 2 significant figures. So the 2 significant figures, it's going to be 9.4 meters per second. And remember to find the angle. I'm running out of room. So to find the angle, it's just going to be 10 to the minus 1 of the opposite side, which is the 2.08655 divided by my adjacent side, which is 9.1. Oh, 9.1. Do I stuff that up? No, I don't think so. Let me know if I'm trying to speed race. So if we do find our angle, it'll be 10 to the minus 1 of our opposite side, 2.08655 divided by 9.1925, and it will give us an angle of approximately 12.79, which is approximately 13 degrees below the horizontal. So we found the velocity, which is what we're after. Calculate the velocity of the ball. So if it just says velocity of the ball after 1 second. So the velocity of the ball after 1 second would be 9.4 meters per second at an angle of 13 degrees below the horizontal. Finally, some problem solving questions. Have we got questions 1 to 3 in the textbook on pages 16 to 19? Thank you.